Our first presentation is entitled Advanced React Fitness Training Aid. The advisor is Dr. James Brooks, and without further ado, I'll pass the presentation on to that group.
Can everyone hear me?
Sounds fine.
Okay. Good evening, everyone. My name is Noah Peterno. Alongside of me is Caleb Miller, Stephen Nash, and Asher Ostrowski, and we are the Advanced React team. Now, each member had critical roles to play when working together on our project. Asher was in charge of coding our Raspberry Pi, along with doing testing and development on our sensors. Stephen was most helpful in the area of software, being the only CE out of us other three EEs. Caleb contributed by taking care of our budget, preparing us for Venture Battle, and assisting with hardware development. Finally, I was responsible for developing our hardware, designing our charging case, and keeping firm documentation. The greatest moments in sports typically occur when an athlete of one team reacts quicker than their opponent to complete an action for their respective sport. In football, this was the case for Malcolm Butler in Super Bowl 49, when he intercepted a pass from quarterback Russell Wilson with less than 30 seconds to go in the game. In basketball, we can also consider LeBron James, who arguably made a championship-saving block to opponent Andre Iguodala to win the 2016 NBA Finals. Finally, if you ask any tennis player, they'll tell you that the ability to anticipate where their opponent will return the ball and react accordingly makes all the difference to win a match. Reaction time is an incredibly important key to winning in sports. So when Dr. Buxton and the athletic department of Grove City College approached us to develop a system that would improve our athletes' reaction time, we started brainstorming. Here's the system we comprised over this academic year. Our system can be best described as a fitness training system that involves three different elements. The first of which we can refer to is our pucks. Our pucks are basically the computers of our system, and they're enclosed in a PVC end cap. They utilize a Raspberry Pi, which collects and stores workout data, and also controls our LEDs, piezo buzzer, sensor. It features a 3.7 volt battery to power the system. The second element is the app. Our app allows users, such as our athletes and our coaches, to select pre-programmed workouts or to create their own customizable work. It also allows them to view their workout statistics in real time and gives the opportunity for coaches to quantify their athletes' progression in their respective sports. Of course, our third and most important element in our system is our athletes. They are the ones who are participating and utilizing our system to improve their reaction time so that whenever they step on the field or court, they are better prepared to defeat their opponents. To give you all an idea of how our system works, the next image will illustrate this a little more effectively. This is a classic example of what we envisioned a workout with our system to look like. For example, an athlete might start at position 1, and after a short countdown, the system would trigger one of the other pucks to light up with an LED. The athlete would quickly have to find which puck to run to, and when he or she reaches that puck, he would have to swing, whether it be by his hand or with a tennis racket or some other necessary equipment, over the puck within a close proximity. When the sensor in the puck would recognize it, it would sound a buzzer, prompting the athlete that he or she has completed the action effectively. Afterwards, the athlete would have to look around and find which next puck is prompted and run over and do the same thing. And this process would continue until the programmed workout had been completed. So with that being said, we had a lot of requirements to make sure that we were handling. So after discussion with Coach Buxton, these were the requirements we derived. So in regards to the puck, we wanted the puck to feature wireless communication between both the pucks and the app, over a span of at least 20 feet. We wanted the puck to be able to prompt our athletes with the stimulus of sight and sound, which would be accomplished through the LEDs and the piezo buzzer to our workout participants. We also wanted the system to be able to withstand the normal practice time, and so we figured it would be a good idea to have the battery life be able to withstand at least an hour. The system would also need to be able to endure accidental blunt force. We understand we're working with athletes, and anytime you have athletes that are swinging things, accidents happen. So we wanted the system to be robust enough that it would be able to handle that accidental force. We also wanted the system to be transportable. We needed the pucks to be able to detect these swift motions, as I said before, from the athletes up to about 6 inches away. That's about how precise we wanted it to be. And we wanted the system to be able to be charged in a convenient method. So we chose micro USB cords to be able to charge that. For the app, we wanted them to feature a graph to display meaningful data, such as workout plotted reaction time. And we also, like I said before, wanted the app to feature both pre-programmed workouts and a create your own workout option. And last but not least, we wanted the system to be able to travel well with a travel case. So we designed one in order to both store the pucks and to make an easy way to charge. So at this time, I'm going to move on to Asher Ostrowski. He's going to be explaining our first prototype and the progress we made during the fall.
This video shows the initial prototype in action and the communication between the puck and the app. You can see, as the light is illuminated, the user swipes his hand over the sensor and the data is reported to the phone. We conducted multiple tests on each of the sensors. These tests involved range measurement, speed measurement, environmental checks, and material checks. The environmental check tested what environment conditions the sensors worked with. This mainly includes light conditions. The material check tested what materials would trigger the sensor. We checked this because we needed the sensors to be triggered by both hands and tennis rackets. First, we have the capacitive proximity sensor. This picture shows our initial implementation used for testing. This was suggested by Dr. Moore when we spoke with him about what kind of sensors we should use for our project. This implementation used an Arduino to test the idea. We used the Arduino because there were guides on how to create a capacitive proximity sensor with an Arduino. The capacitive proximity sensor measures the capacitance between the plate and the user's hand. For example, as the user moves his hand further from the plate, the capacitance decreases. The data in the chart is the data collected when we tested the sensor with multiple different materials. The distance was 2 centimeters for every object, and the time value is actually a measure of how long the capacitor created by the hand and the plate took to charge. As the time increases, the capacitance increases. This sensor was a great option because environmental conditions did not matter. The range was very good, and the measurement speed was very fast. The only issue with this sensor was that it could not detect a tennis racket on its own. Second, we have the infrared sensor. This sensor works by shining an infrared light, which then reflects off the surface and back into the receiver. The sensor must be adjusted in code to account for the distance between the sensor and the object. This sensor was not used, but we did do significant amount of testing with it. The advantages of the sensor are that it works with any material, the range of the sensor was good, and the sensor worked under any light condition. The major problem with this sensor was that the measurement speed was too slow. This is why we chose not to use it in our first prototype. Lastly, we have the photosensor. This sensor was used in our first prototype as we did not have a version of the capacitive proximity sensor that worked with the Raspberry Pi. This sensor was an attractive choice because it was very cheap, extremely simple to implement, as seen in this wiring diagram. The photosensor uses a phototransistor, which acts as a switch. When light shines on the phototransistor, current is allowed to flow, and when light is not on the phototransistor, current flow is restricted. The measurement speed was basically instantaneous. The range was great and it worked with any material, but it did not work under some light conditions, especially under direct sunlight, which was a major issue. This is why we decided it would be better not to use this as the primary sensor for further iterations of the puck. We chose 802.11 wireless communication as the initial method of wireless connection between the Android app and the Raspberry Pi, as it seemed to be an easier way of connecting the devices. This caused issues with when multiple pucks were involved. We would have needed a host puck, which is possible, but it made everything more complex. We reassessed Bluetooth as an option and found that it was much simpler, as the app is easily able to connect to multiple devices. The initial app used the mentioned 802.11 communication protocol to communicate with the Raspberry Pi. The app allowed the user to trigger a workout session remotely and also read back and graph the data in real time. This was partially shown in the video and is shown in this photo. We chose a piezo element as the speaker for our initial prototype because it was cheap, low power, and convenient, as there were spare piezo elements in the lab. There were problems with using a piezo element as a speaker because the piezo element was built for an Arduino, which is slightly different at an architectural level from a Raspberry Pi. The incompatibility of the speaker with the Raspberry Pi led to the speaker sounding awful. This was because the piezo element required a square wave, and the wave we could produce with the Raspberry Pi was dirty due to software differences between the Pi and the Arduino. We chose the Raspberry Pi W as it was small, easy to program, cheap, and had wireless capabilities. These capabilities included 802.11 and Bluetooth. We used Python as it was the coding language we were most comfortable with, and it was one of the default languages available on the Raspberry Pi. The coding was relatively straightforward, and the most notable part was disconnect handling. This made sure that the code did not crash if the app disconnected from the Pi. The Pi on disconnect would just wait for the app to reconnect, which is very important in a system that needs to run continuously. Now I'll hand you off to Stephen Nash, who will talk about prototype 2.
In this prototype, we focused on switching to Bluetooth, implementing the capacitive proximity sensor, building the carrying case, and continuing to improve the Android app. For our second prototype, we tried implementing Bluetooth again. This time around, we found it to be more reliable and easier to implement than 802.11 Wi-Fi. One requirement was to be able to have around a 20-foot wireless range between the app and the pucks. When we tested the range of Bluetooth, it exceeded that requirement with a range of around 300 feet. One condition for this range was it had to be line of sight between the phone and each puck. Obstructions such as people or smaller objects were no problem. It was larger obstructions such as buildings and cars that would shorten the range to be less than 300 feet. This range would allow pucks to be placed all around a tennis court, football field, or track, so coaches can create bigger workouts. Lastly, it was easy to implement with multiple pucks. This was because an individual connection was made between each puck and the app. There was no need for a network to contain all the pucks. Each puck would be paired with the phone on its own. Adding pucks to the app would be as simple as pairing a phone with a new speaker. The capacitive proximity sensor. We had two main problems with the sensor in the previous prototype. First was that the sensors were affected by environmental light. Second, the sensors were not capable of detecting objects moving very fast. The only sensor that was left was the capacitive proximity sensor. The drawback to using this is that it could only detect conductive material. The main concern is that tennis rackets are not conductive. After talking to Coach Buxton, he said it would be fine if tennis rackets required a small strip of metal, sort of like tinfoil, to be placed on the racket in order for it to work. Once that concern was addressed, we decided that is the best sensor for our final product. We implemented it using the Raspberry Pi rather than the Arduino. In this picture, you can see the sensor as well as the piezo element connected to the Raspberry Pi. The sensor is very small and needed to be connected to a metal plate. For this prototype, we added a battery and charging circuit. The battery was 3.7 volts and 2,500 milliamp hours. Powering the Raspberry Pi and the sensor, we found one charge would last us over 3 hours. This test was done while the Raspberry Pi was connected to the app via Bluetooth, and the Raspberry Pi did some calculation every 30 seconds. We also used the charging circuit that would connect to the battery to the Raspberry Pi. If we still had access to the lab, we would have hardwired the charging circuit directly to the Raspberry Pi. The charging circuit also allows the battery to be charged using micro USB. The main purpose of the carrying case is to protect the pucks and make it convenient to carry. We had foam cutouts to protect the pucks as well as a hard plastic exterior. An extra feature we wanted to add was being able to charge the pucks while in the case. We did this by adding a wall plug to the case and using USB wall socket for all the pucks to plug into. You can see that in the left picture, the USB sockets where the pucks could be plugged into in order to charge. In the lower right picture, you can see the cord that would plug the entire case into the wall socket. The Android app improved quite a bit for the second prototype. Here, you can see a screenshot of the home screen. Features like navigation and custom workout were added. Navigation allows the user to move between view data page and start new workout page. Custom workout allows the user to create a workout with a specific order of pucks and change the delay between when each puck is activated. A feature was also added that allows the user to see which pucks are connected. The screenshot shows the connection status of 2 pucks. Last, improvements were made to the graphical interface to make it look more professional. Such improvements include a nicer background color and consistent font. Now Caleb is going to talk about our budget.
Thank you, Steve. In addition to the design aspect of the project, we also had the responsibility of making our project within a budget. Grove City College graciously provided us with a budget of $2,000 to work with. In the last 2 semesters, we kept our total cost at $450, with an estimate of an additional $50 to complete the project. These final estimates come from the cost of the finished puck casings and the PCB prints. But the important thing is that we were able to make our progress while exercising good stewardship over our resources. In creating the budget, we organized our costs into 6 categories: the power, the Raspberry Pis, the puck casings, the testing, the sources of stimulus, and the sensors. For the engineering econ portion of the project, we had the task of using the budget data in several meaningful ways. For instance, we analyzed the data using a sensitivity chart. This representation uses the categories from before and displays how changes in the cost of a single section will affect the cost of the entire project. As you can see on this slide, if the Raspberry Pis were to increase in price by 20%, the project budget would increase by almost 5%. This is a valuable tool when making several of one product, such as our 4 pucks. In addition, we analyzed the data in the form of a Pareto chart. This chart displays the cost and the percent of total for each of the categories. So now it can be shown that the Raspberry Pi with the power system make up 59% of the costs. Also, you can see that an increase to their combined costs of 20% would correspond to 12% increase in the total project cost. This is helpful in seeing which categories of the project are pulling the most cash, especially when we're trying to be frugal. Now, being unable to finish our project, here's how we would have gone about completing our final tasks. Number 1, we would have made sure to stay in contact with our customer, Coach Buxton. Going into the final design stages, it is imperative to stay in contact with the customer. This will help to make sure that he gets a finished product that he is happy with. Second, we had many aspects of the hardware that still needed development, such as the LED system, the soft shutdown, and the PCB spins. The LEDs needed to be incorporated in the puck design as well as the software. The soft shutdown was still in the research phase, so it would have had to been redesigned almost from scratch. And we had completed our first PCB spin. However, it still had to be tested. And once we had finished testing it, we could have continued on to our next iteration. As we had such success in using the design process throughout the project, the key to completing these tasks, as well as anything else that would have come up, would have been sticking to that strength and working through it as we prototype and get to that finished product. Finally, when it comes to testing these final prototypes, it is again imperative that we bring in help. This would be in the form of both Coach Buxton and other athletes. This would allow us to put the Advanced React system through rigorous trials and ensure that that it will hold up while still providing the meaningful reaction time data we're looking for. We would like to extend a hand of gratitude to everyone involved with this project, notably our advisor, Dr. Brooks, our customer, Coach Buxton, and the college itself. In addition, thank you all for your time and attention today.
Thank you, group. What we'll do is open this time to questions. We normally take about 10 minutes. If you have a question, you can pose that two ways. Number one, just post a text requesting opportunity to do that. Or if you like, you can just unmute your microphone and we'll take your question that way. So any questions?
Hi, this is Mike Bright. I have a question in terms of the accuracy. So what was the precision? I swipe over the puck and it's recorded back at the app.
Yeah, so we wanted the precision to be within 6 inches. So the athlete would have had to swing his racket or at least swipe his hand within a 6-inch range of the top of the puck in order for the sensor to pick it up and to trigger the buzzer so that the athlete would.
Yeah, I actually meant time-wise. So, there's some delay in Bluetooth communication. Is this, within a second, within a half a second, hundredth?
I think I could answer your question, Dr. Bright. All our timing was done on the Raspberry Pis. So the time it took for any signals to be sent from the app to the Raspberry Pi it didn't matter because the final result was sent over Bluetooth, not start or stop the timer signal. If that makes sense.
So you had synchronized clocks, is that what you're saying?
No, so when the Raspberry Pi would just get the signal to go, and then it would start its own timer. And then when the athlete triggered the sensor, it would stop its own timer and then send the difference between that to the app.
Mike, any more questions there?
No, I'm good, thanks.
Okay. Just a reminder, students, when you answer a question, if you could unmute your video, transmit your video, as well as unmute your mic, and questioners, you can also broadcast your video too. Any more questions?
Yeah, I do have one. This is Tim Moore. And I was curious about why the infrared sensor was too slow. That surprised me. I'm not sure if there's some sort of low pass filtering going on there or something. What infrared sensor did you try, and do you have any idea why it was slow?
So the infrared sensor had a set sample rate, and we set it as high as we possibly could. But if you swung your hand over it as fast as you could, not as fast as you could, but at a good clip, it wouldn't pick it up because it would happen between samples. So that's why we found that wasn't fast enough, and we couldn't make it go faster because it's all built into the sensor.
Okay, so it was a purchased sensor, and it had actually a sample rate.
Yeah,
Okay.
yeah, that was it.
Thanks.
I had a follow-up question on that. I guess I think what Dr. Bright was asking, and I think what Dr. Moore was insinuating as well, it sounds like you had, for your prototype, about half a second lag maybe between the time, someone would move something and you could record that. Maybe I misunderstood.
I'm a little confused by your question. Could you rephrase it possibly?
Yeah, so if I move the puck or do something that causes that to change, and I move let's say 10 times a second or 100 times a second, is it going to pick that up, or is it going to pick up typically a movement as slow as half a sec to a second, maybe 1 hertz or 2 hertz, because of all your sampling lag and so forth?
I don't remember the exact sample rate that the infrared sensor used, but yeah, that's what we were experiencing. That as soon as you put your hand over it, it would take a second to recognize. Not a second, but it would take some amount of time to recognize, and that's why we ended up not using it, because that time was too big for us to be able to do.
I see. Any other questions?
Yeah, this is Dr. Rumbaugh. Thanks, guys. I was wondering if you could tell us about the networking of the devices, like how many devices were running simultaneously, and how did the host hub handle that? Was there a maximum limit on that?
So the maximum was just however many Bluetooth devices a single device can connect to. So each Pi was its own Bluetooth device, and you can pair it, and then the app would create a socket for each Bluetooth device. So the network itself was only between the app and the puck, and therefore it didn't include any other pucks. So as long as the phone could support more devices, more pucks could be added. And the phone could support, we tried 4, and it supported 4 no problem. And I'm sure it could support more, but I'm not sure what that max number is.
Okay, great. And sorry, a quick follow-up on the Bluetooth. So were you working to some spec for max distance you were shooting for? And did you have any trouble, with your range on the Bluetooth communications outside?
Yeah, we were hoping for a 20-foot range. And I tested it at home, and I just had the Raspberry Pi on one end of my street, and I walked down the street with my phone until it disconnected. And I walked 300 feet before it started to have issues. And then if I walked behind a car or behind a house, it'd have issues. But if people were standing in the way, or something small was in front of it, it didn't have any issues at all.
Cool. And that was just using the built-in Bluetooth transmitter on that Pi W?
Yeah, no extra antennas or anything, just the Pi and just the phone.
Wow, cool. Thank you.
Any follow-up questions? I had a question. Have you looked at other areas or kind of venues you could take what you've done and apply it to other, maybe an industrial application or another sports application or something else where you'd use something similar to what you've created, but for something slightly different in terms of what you're actually using it for?
Yeah, I could probably answer that question. I mean, we primarily were using this project to help out Coach Buxton. Coach Buxton is the head coach of the women's tennis team, I believe. And so we primarily wanted to, focus our efforts on what a tennis workout might look like. So, of course, we got a bunch of input from Dr. Buxton in that way. But the other ideas we were having, I know I'm a former football player, and so I know during the off-season training we would do mirror drills where we would have like cones lined up, so sort of similar to how we had it in the figure there at the beginning, and so it could be used for applications like that. We thought about a 40-yard dash, placing one puck at 10 yards and being able to see the time it would take for the athlete to run over. But as far as like industrial applications and things like that, I don't think we really thought that far ahead. We were just basically focused on the athletic program.
Okay. We have time for one more question, one final question. Okay, hearing no further questions, thank you, group, for that.